Hey. Hey.
Okay. Shall I start? Okay, let's get going. So I'm going to present the paper. As you can see, some theoretical properties of gans. I won't even try to pronounce all the names in the author list, but there they are. Okay, so most of this stuff you already know, but just in case anyone is not on board. So GANs were introduced in 2014. Perhaps they were a little bit earlier than that, but anyways. So they're generative models, and they're meant to be capable of generating images that humans would deem as authentic. Perhaps they're not the best at the moment, but they're pretty good. And the idea is to use samples from some unknown distribution P star to generate samples from P star. So the main idea is that you go to competing networks, hence the name A for adversarial, and they're competing. There's one network producing counterfeit images, and there's another network, discriminator network, that is trying to tell the fake images and the authentic images apart. And essentially, you're training both networks using SGD or something like that iteratively. So essentially, it's sort of like a game, and there's like a subtle point. The optimization is very, very hard to analyze, but they seem to be working fairly well. The nice thing about it, at least what I liked about this paper, and what I think is very nice about GANs compared to other methods, like, for example, is the fact that they've got the built-in discriminator network. So if you think about what makes an image look like an authentic image, there's probably many ways to do this. There's many ways to try and test whether an image looks authentic. You can design maybe metrics or norms and things like that. At the end of the day, as a human, when you look at an image, you don't look at a bunch of images and you say, okay, these are authentic or not. You look at an image and you say, oh, okay, this looks realistic or this doesn't look realistic. So I think the idea of having a discriminator is pretty good. And we will see, the nice thing about this paper is that they managed to link it to some proper statistical distance, so that essentially training the GAN is, at least in an idealized scenario, it does have very strong statistical meaning. Okay, so essentially the optimization is solving this empirical problem. So there's a lot of notation I'll go through in a moment. So it's a nymph over the parameter space of the generator network, and it's a supremum over the parameter space of the discriminators. And then essentially that's a form of cross entropy loss. So D is the discriminator. So it's taking an image from some set, so X in a set E, which we assume to be a subset of Euclidean space RD, with D potentially very, very high. And it's outputting a number between 0 and 1, which we interpret as the probability that the image is coming from the true distribution P star. Okay, so for example, if that is more than a half, then we would classify that as being an image from the true distribution. If it's less than a half, we classify it as being a fake image. So we've got a true sample x1 up to xn coming from P star. Again, we assume all probability measures are absolutely continuous with respect to some reference, because they're so there may be probability measures on different spaces. I'm going to write new for all reference measures, so think of it as Lebesgue or whatever you like. It's not important. It is, but it's not important for the results I'm going to talk about. Now, all fake samples are essentially generated by taking IID instrumental variables from some lower dimensional space. So some distribution P0 on RD dash, where D dash is usually much less than D. And these may be Gaussian or uniform. And then we push them forward through some mapping, which is from through a parametric family of mappings, G theta or curly G is the whole family, that are mapping from the lower dimensional space back into the space of interest, which is E. So we can equivalently parameterize, rather than the mappings, we can parameterize the push forwards. So we write curly P for that. And in some cases, you can get better results if you think of the push forwards, because they sort of discount identifiability issues. For example, multiple parameters may give rise to the same distribution, and in those cases, it will be impossible to actually prove something about theta, but it's possible to prove something about p theta. Now, the discriminators are again a parametric family. They're a subset of Borel maps from E to 0, 1. So d alpha will correspond to some parameter alpha and some set lambda. And however, we will also consider the set of all Borel mapping from E to 0, 1. It's a nice idealization that gives us some results. Okay, so we can equivalently restate the problem in this form. So we're looking for a theta hat such that the empirical loss L hat, now we've taken the log, it's equivalent. The empirical loss at theta hat D, we take the supremum over D, that is less than the supremum for any other theta in the parameter space, okay? G theta Z i's are again the counterfeit samples, and essentially the starting point of this paper, which was also mentioned in the original GAN paper, is to make a first abstraction by looking at the population version, okay? So we ignore the samples, we look at the population version of the problem. So that's one essentially approximation or abstraction that we're going to make. The other abstraction that we will be making several times is by considering ignoring the fact that the discriminators are coming from a parametric family and considering all possible discriminators, okay? Both of them are useful generalizations or assumptions, and then they help us get some actual results and link it to a proper statistical distance. Okay, so D infinity is the class of all Borel mappings. And for a fixed generator theta, the nice thing about considering all discriminators is that if we take the supremum over D, obviously we can bring the supremum inside the population loss, so inside the integral, to get an upper bound, and then we can optimize that pointwise. So for every x, we can optimize that quantity with respect to dx, and essentially what, yes? Oh yeah, so ignore the second integral. So everything is in brackets, right? Yeah. And the d mu is outside, so ignore the second integral, it shouldn't be there. Yeah, so there's just integral with respect to x, which is coming from some reference measure mu. So if you optimize this, you get the optimal classifier, the Bayes classifier, which is optimal with respect to the cross entropy loss, okay? So we call that d theta star, and the star is a superscript on the d, okay? So for every theta, this is the optimal classifier with respect to the cross entropy loss. Okay, so what's nice about this is that now we can link it to a statistical distance. So essentially, take this classifier take any theta, take this classifier, the optimal classifier for the corresponding theta. You can do this calculation. Essentially, what you get in the end is you get the KL of p theta with p theta plus, so with the equal mixture between p theta and p star, plus the KL of P star with the equal mixture of P and P star. And that's actually a divergence. It's called the Jensen Shannon. It's like a symmetrization of the KL. It's not the only symmetrization. And the cool thing about it is if you take the square root of that, it's actually a metric. Okay? So essentially, if you look at the population loss of that you achieve with the generator theta corresponding to the parameter theta and the optimal classifier d theta star, so the optimal classifier for that theta, that's equal to twice the Jensen-Shannon divergence between the generator distribution and the true distribution P star minus a constant. So that's the natural logarithm of 4, okay? So essentially, we can think of the empirical problem that GAN solve from the point of view of optimizing the generator network as essentially an approximate empirical version of why is the yeah, okay, so it's an approximate empirical version of trying to find, of projecting P star with respect to onto the available classifiers with respect to the Jensen and Shannon divergence. Okay, obviously it's empirical because we only have access to samples, and it's approximate because we have essentially approximated the true population problem with that where we have access to all possible classifiers. Okay, in practice we won't have access to all classifiers, so it will be an approximation. Okay, so the first theorem they prove, which is theorem 2.1, essentially states that under some assumptions, the optimal discriminator is unique. Okay, it's unique on the set, on the complement of the set where both densities are equal to 0. So if essentially the probability that they're both equal and equal to 0 has measure 0 with respect to the reference measure, then essentially you've got a unique optimizer, an almost surely unique optimizer on the whole space. Okay, so the proof is fairly simple. Once you get your head around a few things, essentially what you do is we assume that theta achieves, so we assume that the discriminator achieves the same loss for the parameter theta as the optimal classifier. And then essentially the difference of the two losses is 0. And on the set where both distributions are 0, the loss is actually 0. Because if you look at the particular of the form of piece of this function f here, which appears in the cross entropy loss, p star and p theta are 0 in this set A. So essentially we can drop the set A from this integral, and essentially we've proven that the expectation of the two population losses are equal on the complement of the set A. And then essentially you use the definition of the optimal classifier, and you can prove that in fact this thing is non-negative. So this thing is non-negative and its expectation is 0, then the two must be equal almost everywhere on the complement of the set. If essentially the complement of the set has full measure, then you're done. You've proven that the classifier is unique. Okay, so I guess the reason for it's important to know that it's unique because essentially the way the paper progresses by fixing first the optimal classifier for any theta and then solving the optimization problem for theta. Whereas if there were multiple optima for the classifier, then essentially you'd have to try to solve multiple optimization problems, one for each optimal classifier. So essentially, first you fix the optimal classifier, then we analyze what happens with trying to optimize over the generator, and then in the end we will see we will start removing the layers of approximation and try and get a bound on the loss that is actually achieved in practice. Okay, so why is the Jensen-Shannon formulation important? Now, if we did have access to all possible discriminators, then we can define the optimal generator parameter theta star by that inequality 4. And because we know that as soon as you put in the population loss, the optimal classifier for that particular theta, then we've got the Jensen-Shannon divergence. So essentially, the superscript star here refers to the discriminator, and theta star refers to the parameter. So what we're doing is theta star is the parameter such that the loss, the population loss achieved when you pair that with the optimal classifier for that theta star, then you get a population loss that's less than the optimal loss achieved for any other theta. Okay? So, and now we can link that to the Jensen-Shannon. So essentially, it's a projection. So if we had access to all classifiers and essentially when we were training, we were allowed to essentially optimize in one step the classifier, which is again not done in practice. It's not possible in practice. Then essentially solving the problem with respect to the generator would be projecting P star with respect to the Jensen-Shannon. So obviously in realistic scenarios, we can't assume that P star is in P. Because obviously, again, so if this was true, then the rest of the analysis would be not useful at all. It wouldn't really tell you anything because the optimal classifier would just give would be equal to a half. And the other thing, obviously, in realistic scenarios, we don't have access to this. So, okay, we will see, however, how that we can bound the approximation error. Okay. So the second theorem in the paper is about the uniqueness and the existence of the optimal parameter theta star for the generator network. So we need additional assumptions here. So we assume that the family of distributions we can produce through our generators is compact and convex with respect to the metric delta, which is the square root of the Jensen-Shannon divergence. Now, if P star admits a strictly positive density with respect to our reference measure, then there is a unique P bar, so a unique probability measure that minimizes whatever should be there. So essentially the population version of the problem. So obviously I'm missing the objective. But you can also replace it with the Jensen-Shannon divergence between P, so little p, and P star. Now, the parameter itself, as I said earlier, it may not be identifiable, so P bar may arise from multiple parameter values. However, if we look just at the push forwards, then essentially the proof follows by convexity and compactness. So compactness, essentially, assuming compactness, we can prove existence from continuity of the mapping, sending a probability measure to its Jensen-Shannon divergence from P star. Continuity itself follows immediately from the triangle inequality because this delta metric, the square root of the Jensen-Shannon divergence is a metric. So continuity of this mapping is pretty much straightforward. The only thing you need to prove is essentially that it's lower bounded, which takes a little bit of work, but it's fine. And then the rest of the work in the proof is to prove uniqueness. So essentially, to prove uniqueness, you use convexity. We've got a convexity for the function over there, which is essentially if you plug, if you replace z. Okay, so all x's should be z on the right-hand side of the definition of fa of z. So replace all x's by z's, and then it should be correct. essentially you can write down this Jensen-Shannon divergence in terms of this function f, where the parameter a is p star, okay? And when p1 is different to p2, then we can use convexity on this part of the integral. So the only reason we're decomposing it is because if p1 is equal to p2, then we can't really get a strict inequality. But on the complement of this set, we can use the strong convexity or strict convexity of fa, and essentially then everything is pretty much straightforward. So we go from convexity of this function, from strict convexity of this function, to convexity of the Jensen-Shannon divergence. Okay, so and then uniqueness of the minimizer follows from strict convexity. Okay, so now we will start removing the layers of approximation. So the first layer of approximation is having access to the full set of classifiers. So let's assume instead that we have access to a parametric family of classifiers. Now we can no longer define P star according to the, obviously, we can't assume that we have access to the optimal classifier because to compute it, we need access to P star, okay? So that's why it's too much to assume. And we can't, and in practice, we won't even assume that we can approximate it perfectly within our class, but anyways. So we assume access to a parametric family of classifiers, and now we have to redefine what the optimal parameter for our generator network is, because we're solving a different problem. So we want to optimize theta with respect to this new objective where the supremum is taken over the parametric family rather than the full set of discriminators. So we call this theta bar to distinguish it from theta star. And the idea now is that if we assume that our parametric family of classifiers can approximate fairly well the whole class of Borel Borel classifiers, then the closer we can approximate the full set, then the closer this theta bar should be to theta star. Okay. Now the next theorem will impose an assumption under which we can quantify this. Okay, so the assumption is the following: for every epsilon positive, there exists an epsilon positive and an m between 0.5, and we can find a discriminator in our parametric family curly D that also belongs to L2 with respect to mu, such that we can bound the classifier above and below away from 0 and 1. Yep. So essentially D, it cannot go out arbitrarily close to 0 and cannot go out arbitrarily close to 1. And D approximates the optimal base classifier for the optimal parameter theta bar. Okay, so theta bar now refers to the optimal theta with respect to the parametric class. However, D star is the base optimizer for that theta, for theta bar. And we can approximate it within epsilon. Okay, so yeah, so theta bar is essentially we've removed one layer of approximation. However, D star is still the optimal discriminator. So D theta bar star, or D star theta bar, does not necessarily belong to the set of available classifiers. However, the reason it's useful is because it allows us to link this result back to the Jensen-Shannon divergence. So assumptions are the following: we've got some positive capital M such that we can bound the true density P star and the density of the distribution generated by the optimal theta bar. We can bound their densities with respect to the reference measure above by capital M. And under that assumption, where essentially the epsilon we're using is less than 1/2 capital M, there exists some constant depending only on little m and capital M, such that the difference between the Jensen-Shannon divergence between P star and the optimal P theta bar, that's the optimal in the limited class of classifiers that's available to our model. The difference between that divergence and the divergence between the optimum the true P star and the optimal distribution with respect to the full set of classifiers. So then that's bounded above by C epsilon squared. It's also positive. Positivity follows from the fact that this distance is always less than that just by definition of theta star, okay? Because theta star is essentially optimizing this problem, whereas theta bar is optimizing a slightly different problem, okay? So, yes? No. I mean, the reason is, I'll explain it later, they even say it, but the reason it's not reasonable is because you don't know what theta bar is in advance. So it's not a reasonable assumption. Okay, so I'm stating the same theorem again. Now, it took me a while to understand why on earth this is useful. Maybe it's obvious to everyone else, but just in case it isn't, I'm just going to go through it. So essentially what we've done is we've compared the Jensen-Shannon divergence between P star and the optimal within the limited class of classifiers available to our model, and the Jensen-Shannon divergence between the true distribution and the optimal with respect to the full set of classifiers. Okay, now we can link this quantity back to the we can link the population loss that is achieved by any theta against the base optimal classifier to the Jensen-Shannon divergence. So essentially, once we put this here, applying essentially this identity with theta bar and theta star, essentially what we get is that the population loss achieved by theta bar, so that's the optimal in the limited class of the population optimum in the limited class of classifiers, is actually quite close to the optimum with respect to the full set of classifiers, so theta star. And the distance is only is bounded above by 2 times this constant C times epsilon squared. Okay, so what does this mean? So essentially, we can start putting all the supremum in. So this is the theta bar and so on and so forth. This is essentially this would be the Jensen-Shannon projection of our class of generators onto the the projection of the true distribution P star onto our set of generators. So essentially, the parameter theta bar that we're finding if we use a limited class of classifiers achieves a loss that is within 2 times C times epsilon squared of the best possible loss. Okay, so that's essentially what we're saying. So solving the problem within the smaller class D, or within the full class of set of classifiers D infinity, only makes a small difference of 2C epsilon squared if you're interested in population loss, okay? So essentially, we're trying to control the change in population loss by approximating the set of classifiers by the full set of classifiers. Okay, and as promised, assumption H epsilon is a little hard, where little is an understatement to verify since we don't know what theta bar is in advance. Okay, sketch of proof. So I'm not sure how interesting this is to people, but the idea is that you can write down the population loss achieved by theta bar for any discriminator D. You can re-express it in terms of the Jensen-Shannon divergence between the true P star and P theta bar, and an additional term which essentially is related to the KL between P star and P theta bar with respect to these auxiliary measures. Okay, so these auxiliary, well, this is, yeah, okay, you know what this is. D mu, so that's the reference measure, and essentially this is the weight, well, it's a mixture times the discriminator, okay? And here is 1 minus discriminator. So these are like weighted versions of the measures appearing in the Jensen-Shannon, of the mixtures appearing in the Jensen-Shannon divergence. So the whole point is we want to make use of the L2 approximation that we've imposed as an assumption. So essentially, the proof proceeds by using Cauchy-Schwarz several times. So for example, here, we can bound the difference between this integral and 1 by Cauchy-Schwarz. We're using, so this M here is coming from the fact that both densities are assumed to be bounded above by capital M. This is the approximation assumption, so epsilon. So essentially we can go through. Now, by controlling this term, essentially we have controlled this quantity here. Okay, now we have to control the KLs. Again, the KLs, we want to bring the L2 error, so we bound the KL with the chi-squared distance, and then we use Cauchy-Schwarz, and the rest is not hugely interesting. But the idea is that once you've bounded this quantity here, then you can start linking again the population loss achieved by this theta bar for any discriminator D to the Jensen-Shannon projection of the true distribution onto your parametric class. Okay, right, so now we've essentially controlled the error that is produced by the approximation of our parametric family of classifiers with the full set of classifiers. So now the second layer of approximation is the fact that it's statistical because we've replaced the population, the empirical loss with the population loss. So now we will see what the statistical loss is, the statistical approximation error is. So we've got a parametric family of discriminators. We've got our assumption. So essentially we can find, okay, we will strengthen this assumption. So there's this H epsilon dash. So I like the fact that in the paper they say we slightly strengthen the assumption by going from assuming it for the optimal theta bar, which we don't know what it is, to assuming it for all theta, which is only a slightly stronger version of the assumption, I guess. Okay, so yeah, okay. So we can approximate the optimal classifier for all theta within epsilon, and this we can approximate with the classifier that is bounded away from 0 and 1 by this number m. Okay. Right, and this is the theorem. So under these assumptions, and there is additional regularity assumptions which are imposed as there are differentiability assumptions on the loss function. They're not on the loss function, they're essentially on the full population loss. So there are differentiability assumptions on the log densities. So essentially the total error, the total difference between the expected so theta hat is the optimal for the empirical problem within the limited class of classifiers. So the expectation is over the randomness in theta hat. The second object doesn't really need an expectation, so you can remove that. So the difference in expectation is of order epsilon squared plus 1 over root n. Okay, where n is the number of samples. There is a constant, obviously, there, and it scales like the total number of parameters in the two neural networks. So p plus q, if p is the number of parameters in the generator network, and Q is the number of parameters in the discriminator network. Okay, again, why is this useful? So we go back to essentially using the optimal classifier for this theta hat. So in expectation, the population loss achieved by our optimal theta hat is only epsilon squared plus 1 over root 10 away from the optimal loss achieved by taking the full set of classifiers and minimizing the population loss over the full set of generators available to us, and so on and so forth. So essentially, you can, the expected population loss, sorry, this population loss, or is this? No, the expected population loss is bounded above by this. And this is obviously what we're trying to bound. This would be the, if you subtract the empirical loss, that would be the generalization, right? The generalization. And essentially, this is the optimal we can achieve, plus this would be a bound on the generalization error. Okay, so at least in expectation over the sample, the population loss that we achieve with our optimal theta hat that we computed by optimizing the empirical loss is within epsilon squared plus n to the minus a half from the population optimal with access to all discriminators. So the proof proceeds through essentially uniform arguments. So you control the difference between the population loss and the empirical loss over all parameters. That's why you pick up the P plus Q, because essentially we're working through the extended parameter space where we've patched together the parameters of the generator and the parameters of the discriminator, and it uses metric entropy, so it's not surprising that we get the dependence on the dimension. The rest is just using, if you've read Van Handel's notes, it's just chapter 6. So the regularity assumptions they impose is essentially to be able to say that this process is sub-Gaussian. Okay, so they assume everything is bounded, they assume everything is differentiable enough to be able to say that this is a sub-Gaussian process, and essentially that's the essence of the proof. So they also have some empirical results. So essentially here they train the GAN, and they prove that indeed the Jensen-Shannon divergence is decreasing until it pops up a little bit again. But sure, it makes sense. And so this is actually a nicer, because you can see that, so this is the discriminator. Now the optimal discriminator should be equal to a half. Obviously this does cross a half a couple of times, but it's never equal to a half. And they're only using a discriminator of depth 2. I'm not sure how many parameters they're using, but the depth is 2. And here they're using a deeper network for the discriminator, and you can see that at least away from the tails of the true distribution, the discriminator is pretty much constant and equal to a half, which is pretty interesting. Well, it seems to be working already pretty well. So this is an incomplete. Well, it's complete for the context of the talk, but obviously, if you're interested in this further, read the list of references in the paper. So what I found most interesting about about GAN, so it sort of made me respect GANs a little bit more, because I like the fact that they've got this discriminator built in, which is sort of explaining, why they produce something that looks realistic, which is not the same for other generative models where, so for example, like diffusion models, sure, the premise is perfect, because if you could if you could solve everything perfectly, then you would be generating from the correct distribution. But after you start doing the approximations, you then end up having to essentially try and control the error in maybe L2 or whatever. And it's not clear that L2 is the correct thing that we should be measuring, because it's not clear if essentially when you're looking at an image, you're computing the L2 error between the image and what in your mind is the true distribution. And if that is below a certain threshold, you think, okay, yeah, this is a cat. So the discriminator is potentially a much better measure, and potentially it offers alternative ways of measuring quality of sample. So, for example, maybe if in diffusion models, there is a way to analyze as you're training the model how the optimal, obviously we don't have access to the optimal discriminator, but perhaps we can think of empirical versions of that and how that is evolving. Anyways, that's it. I managed to create 45 minutes out of that sort of thing. Or waste 45 minutes out of that.
How does the idea of like mode collapse factor into this idea of like minimizing divergence? Because I feel like when you look at the objective itself, you feel like if there was a generator that just generated a specific image from the trained data set, then like the discriminator would not be able to tell it apart. Then that seems to minimize the objective, but I feel like if you're looking at the distribution divergences, it would be.
So it would minimize the empirical objective, which is the actual objective that you're minimizing, right? But if you, but compared to but in the population version, it would probably not fare very well, because you mean just generating essentially from the sample, right? So just
just like generating like one or like a specific mode.
It would probably not do very well for the population version, which is an approximation, to be fair, right? So, but if you look at this Jensen Shannon thing, I don't think it actually factors mode collapse at all, right? Or does it? So if you're doing KL, isn't mode collapse explained by the asymmetry of the KL?
Like with one way around.
Yeah.
But then, I feel like you're using Jensen's Shannon.
So it's not explained at all, which I guess it's because this whole thing is based on, mostly the population problem. I don't know.
Because it seems like in practice that's like an issue. And so like going from the empirical to the population seems like quite a big jump that you're
like
a large part of the dynamic.
But I guess so. Okay, so where would it be hidden? So that would be the statistical error, right? And so do you have any idea if mode collapse gets worse with as the parameters go up or not? So I don't know. I mean, I think in practice, like the statistical error would be massive. I mean, you won't be able to explain it for very large sets, because for very large networks, because the constant would probably destroy the root n. So in practice, you would have many more parameters than samples, right? Yeah. So that's essentially very bad. But on the other hand, perhaps there's better ways to bound this, not using uniform things, but so if you had mode collapse, the discriminator wouldn't be able to tell it apart, would it?
Because I guess if you're just looking at samples.
Okay.
So what is this collapse?
I think Andrew can explain it better than I.
Like, I guess in the objective, you have the generator trying to generate images that the discriminator cannot tell from real or fake, but there's not really something inherent there that requires the generator to generate all valid images. If it just generated one good image over and over again, the discriminator wouldn't be able to tell if it was from the data set or not without having some like average over all the things that the generator generated. So it's like kind of issue with training dynamics where you get this issue with the generator just generate specific.
I think the other approximation which is done here, which is very important, is the fact that they ignore the training dynamics, which is perhaps where it's coming from, and that's where it could be factored in, because once you, so here essentially they fix theta, they optimize fully over the discriminators rather than doing a gradient step and then doing a gradient step and then so on and so forth. So you completely avoid like potential issues with like saddle point and things like that. And perhaps that's where it's hiding, because yeah, I guess that's another layer of approximation that's it's totally ignored by the paper, and maybe that's where you know, the issue with mode collapse is hiding. But yeah, it's just a proof of concept type of thing. The nice thing is it links it to this like statistical. Well, it's not new. It was already present in the original GAN paper, but anyways.
Okay, thanks a lot.